Good afternoon. I'm really excited to introduce our guest today, Emmanuel Vercruysse. So Emmanuel directs or is the co-director of the Design Plus Make program at the world-renowned AA, the Architectural Association in London. And there he explores this sort of magical intersection between this sort of the idea of which I think is at the heart of design build, this sort of transmutation of ideas into physical things that exist in the world. Just a little background: he studied furniture design and architecture. He has architecture degrees at Bartlett School of Architecture, and I think this exploration of furniture and craft and making, and then his architectural background gives us a clue that he's probably equally comfortable in the thinking about the intuitive concepts that come through physical making, as well as the sort of technological advances in some of the most latest digital technologies. The home of the AA Design Make program is a really interesting place. It's a woodland, Hooke Park. And so here he is operating at this kind of intersection between architecture, forestry, industrialization. And so I think I'm really excited to see how that informs the sort of thinking and making and the merging of craft and ideas. What I think really resonates for me, and what I think resonates for all of us here at the University of Kansas School of Architecture, is, again, this idea of the merging of thinking and making. This shift from the sketchbook to the studio, from the concept to the fab lab. This idea that you translate ideas into real materials like wood and steel. And this should be familiar to us because, of course, we have a history of doing this here at KU. We're sitting in a building that was designed and built by our students. And so this tradition is familiar to us, but what I find interesting is the way that each individual and each group within their own spheres and their own contexts thinks about this whole enterprise of design and building in their own unique ways. And so I'm really excited to welcome Emmanuel today to talk to us about the unique ways that Design Plus Make operates. So if you could join me in welcoming Emmanuel to University of Kansas.
Thank you, Chuck, for such a flattering introduction. Oh my days, it's such an honor to be here. Such an amazing culture of making and building programs. So your program here has been doing it way longer than us. So yeah, really excited to kind of show the things that we get up to. And it's fascinating, the conversation, to understand what we have in common and where we kind of differ, I guess. So yeah, I will take you on a little journey to a little forest in the south of England. And I think just to kind of go back to this idea of these programs, this idea where the act of making is central to the design is really important, right? I think most other schools of architecture inhabit a world of simulation. It's a synthetic reality where everything is possible, right? Once you start making something, it sharpens the mind because the physical reality is really important. There's material behavior and there's gravity. None of those things exist in Rhino or any of your Autodesk programs. So that's very important. So I'll be showing quite a lot of videos just because everything is process-based and it's really important to unpack that. But also I will show a little video, a little introduction that really locates the work. As Chad said, we are inhabiting a forest, which is really unique. You know, a school of architecture to have a forest is really exciting, particularly these days where material resources will become critical. Okay. So let's have a look. Sorry, not sure what happened there. Try again. Yeah. No worries, no worries. Technology. Let me see if I could. I'll try and start somewhere about here. Oh, sorry, I can't forward it. I hope that's okay. It's a little route into the forest.
You could email me your presentation if you I would go to your display settings real quick. Minimize it, yeah. And then show only on although it's not doing anything. Well, the video keeps breaking down.
Is it just when the video plays?
Yes, just when the video plays.
Plays for, let's say, 30 seconds.
That's what it was set on.
I remember I've seen the video twice already.
Right. I'm not going to start. I think I'm just going to carry on if that's
Yeah,
okay.
we're good.
Yeah.
Yeah.
Otherwise, we have to sit through that. So,
Yeah, you're right. I was trying to get on paper.
I like the sound track, but it's not that good. Okay, so sorry about that. I will talk about the context a little bit more. This is a lovely island that we inhabit. Kate Davis, she's the head of Hooke Park. She describes this place as a pirate utopia because we are very far removed from civilization. So let me just talk you a little bit. So 330 acres, 150 hectares, but most importantly, 17 different species of trees. The timber each has their own particular specialities and behavior and thing that we could use for. So our mission is to develop the campus. So similarly to the build programs here, our buildings have a function. They will get tested and they will get inhabited, and the environment is really quite challenging. So in this place, it rains 270 days a year. So it's a bit of a challenge there. Now, it's really important that the forest is to understand that the forest is an industrial woodland. So the timber is a crop, okay? We do not make any demands of the forest. We work with the harvesting schedule from our foresters, but students get involved with the harvesting process. They also do the replanting. So we are really involved with ideas of forestry, so really understanding where our material comes from. This is very important. The image that you're looking at here is part of our research. We think the world has a bit of an issue when we're talking about long-term thinking. So we're trying to think about a 100-year forest. So none of us are going to be alive, and this is quite challenging, right? So the image that you're looking at is not a render. It is a LiDAR scan. So we are really interested in contemporary technologies. So we have airborne LiDAR scan helicopters, and we use ground-based LiDAR scans. If you don't know what a LiDAR scanner is, it's like a device that sends out a beam. I can scan up to 300 meters in diameter. I'll show some images later. But it means that this is a living entity that we can scan. It's like taking a fingerprint from the forest. And we could do a dynamic section cut through this forest. So we should say, okay, at 6 meters height, what diameter of the trunk is there? So we could really kind of look at how it behaves, this living entity. Now, this is not a tree at Hooke Park, unfortunately, but I'm using this tree to demonstrate what an amazing designer nature is. As a structural engineer, if you want to build this, you have quite a challenge on your hands, right? But this is mainly how we come across this lovely material called timber. It's really convenient. Industry returns this timber to dimensional timber, so it is known dimensions, X and Y, 2x4, all that kind of stuff. And it's linear, it's straight, and they remove the behavior, right? So they put it through kiln, control the moisture content. So it becomes very predictable, which is nice to work with. At Hooke Park, we are very fortunate that we have our own sawmill. So we can decide if we cut up the timber and how we do it, okay? So we're very interested in looking at the tree as a complete entity. Now, this is a scan of a tree. If 50% of a tree makes it as a building component, this is seen as highly efficient. So we are really interested in these missing 50%, right? Because there is no shortage of demand on these prime timber sections, right? We are really interested in, can we find and develop applications of this waste stream, of this kind of material where not many people are interested in? And we're looking at these geometries and think, well, that's really rather beautiful. Can we work with that, right? And then one thing that you have to understand, like nature doesn't necessarily grow linear. So this is a beech fork. Beech trees, they are hardwoods, they're really beautiful species, but they fork. Now industry doesn't really know what to do with that. Well, they know what to do with it, they just amputate the smallest part, and that remains in the forest. But we know historically that from an engineering point of view, this is very strong, right? So this is an image from the 1700s. So people used to go out with a little template when they build a boat or build a house to look for a particular type of junction or a particular type of geometry. So a lot of these practices we don't invent. We look at historical kind of precedents and we actually interpret them through new technologies. So we think Hooke Park is a laboratory, right? We will go out into the forest and run a hard analysis on this living entity. So we are interested in the root system and the entire part of the tree. Making is central to our active design. So we are trying to limit the amount of time people spend behind a computer inhabiting this synthetic reality. So we will pull them out and engage with the material, right? And it's really important because we think that's where most discovery happens, right? So there are, in broad sense, there's two types of research at Hooke Park. One is natural geometries, so keeping timber in the round right? The interesting fact on that is that, first of all, you reduce embodied energy. But if you look at timber in the round compared to dimensional timber of the same section, the timber in the round is 30% stronger. So the fact that you are removing the timber is like you're actually making it weaker. So that's quite counterintuitive. So that's one part of the research. The other part of the research is engineered timber, right? So we can still slice up the tree and recompose it to something which is stronger than the original tree, right? Glues are really amazing these days. Everything is glued together, from your car to your airplane. It's really quite something. But when we can reconstitute a tree, we can actually align the grain. So this is the name of the game. If you want to do glulam or CLT, cross-laminated practices, you want to be in control of the grain. You want to have grain continuity, and you want to do CLT practices where you need to reinforce it. So this is highly choreographed. Every layer, so this is an A layer and a B layer, and you kind of build them up like a cake to build these really quite complicated geometries. Cool. So we are interested also in manipulating the timber. So we can steam bend it, and we can have digital information bending it and controlling it. We can use fire to manipulate it. So we can kind of almost like, if you look at this, this is almost like drawing with timber. Right? So it could be really sophisticated. Right? There's a couple of tools that are really important in our toolbox. One of them is scanning, like photogrammetry or LiDAR scanning. So you all have a smartphone, you take 60 pictures, run it to Agisoft, gives you the 3D model. It means you have a digital twin, okay? So you can do operations upon this digital information. But this is a LiDAR scan of a whole building. So you can do these incredible dynamic section cuts. So you can measure from that and learn from it. This technology is really important for us because we want to see how our buildings behave. So we will scan our buildings through their life cycle and understand how it moves and changes, where there's failure, all that kind of stuff. So it's a really important tool. It also allows us to develop a library, right? So for this project, we scanned 270 trees, put them in a library, wrote a lovely little script, put the trees in front of the robot, and then we could start constructing. We use digital technology to introduce precision only where we need it. The tree and the timber can do all its magic wherever it wants to. We only introduce the precision and the connection details. By the way, this is Latoya. These are 6-axis robots. Most schools of architecture have one. Latoya is older than pretty much all of you. He's a dinosaur in the world of robotics. He's last century. Which means the operating system is Windows 95, which is wonderful because it's all open access. It's not behind paywalls, all that kind of stuff. What we like doing, and we're very proud of this, is we make our own tools, right? So this is not a standard end effector for a robot. So we buy secondhand bandsaws on eBay, and we will reconfigure them, right? So we will learn from the tools. So this is the second generation bandsaw. And then we learn from it, and then we make a new one. And this is the third generation bandsaw. So you can see it becomes really more compact. So we learn from its behavior. This is by far the scariest tool I ever put on a robot, which is, circular saw, revs at 25,000 revs a minute, which is very scary. It's a large part of my research to develop robotic applications. I try and introduce one every year. Any tool which is commonplace within timber production is game to attach to a robot. We attach one every year, as I said, and then what we do is we invite people from all over the world to come and play with this new tool because we need some bright minds and different eyes to look at the tool that we just made. And to attract people, we make a little video, and I'll show you one of them. Fingers crossed. really excited. So I think this is a really interesting juxtaposition between natural geometry and really precision cut scarf joints, okay? And it allows us to build quite crazy structures. So we're really interested in using everything from a tree. When students join us, they don't necessarily have all the knowledge, so we do these first warm-up exercises. So in this case, we gave them this beautiful old root plate of an oak tree that we pulled out of the forest, and we said, can you make a table out of that? Right? So we teach robotics to this. So we scan it, we put it in front of Latoya, he cuts this lovely little lip, and then kind of within 3 weeks, we have a beautiful kind of meeting table. It's quite nice, like a little island coming through the thing. So there's some poetic notions within the design as well. So making is central to what we do, but the drawing is very important as well. Like the drawing is a provocation, and it's like we want really beautiful sketches because they seduce you to go into workshop and try and make them, okay? And we often say our buildings are a site, they are a byproduct of what we mainly do. The main currency is education. We ask all our students what kind of practice, you know, how do they see architecture? What kind of practice do they want to set up? And I'm going to show you one example of one of our lovely students, the chap in red, he's called Empire. I sat on the campus, so it took him about 12 months to figure out how to do this, right? And here he is with his compatriots doing that. And we are now 15 years later, and he's still doing it. He's in Taiwan making these most amazing kind of constructs, fit-outs for shops and windows, and structures within the forest. So this is a really important thing where we try and encourage people to take risk and develop a new practice, right? Okay, so that's kind of setting out the stall of the things that we do. So I want to show you a couple of projects of how we go about doing that. And I'm going to start with the field station. The field station is an observatory. It's a really important location at the edge of the forest. We can look over the landscape. We are just 20 minutes from the coast. The coastline is UNESCO World Heritage. It's a Jurassic coast. It's full of fossils where they found lots of dinosaurs, all that kind of stuff. You all know this machine, an industrial harvester. There's this really intelligent machine roaming the forest. It will cut down a tree in less than a minute. It'll grab the tree, the chainsaw cuts it, flips it around. There's this amazing head that cuts all the branches off. As it's moving, as it's cutting it off, there's potentiometers within the head that are measuring the diameter. On its way back, the algorithm, which is informed by market values, has already calculated the optimum length for this piece of timber. So it's highly automated, it's very fast. This is the aftermath, right? So there's lots of residue material. So we are really interested in these waste streams. So we go, hey students, can you make a building out of this? So here they are, out foraging for material and scavenging through this waste material. So we are interested in this humble beech branch. It's like 50 to 70 mil in diameter, 3 inches for imperial. And the structure, like we wanted to make a 100 square meter roof structure with this, okay? So this is the kind of the diagram. We will use a tree as a column. We have 2 grids of dimensional timber that combined with the diagonals makes this truss frame. So the engineers always correct me, it's not a space frame, it's a truss frame. So I have to think a little bit about it. So all these diagonals, that wall is performed by the timber in the round. So in order to do that, we had to come up with a robotic application. So we made a feeding station. No one wants to be with Latoya when she's in full swing, okay? We gave her one eye so she can see what she's doing. And then we mounted circular saw on the lathe, as you do. Okay. So let me show you what that looks like. So the structure light is not a visual gimmick. circles so we can connect all the center points, and then we have a central line. That's really what we're after. Okay. So this piece is to all work as a repeating component. They have to be all the same length, and they're in compression. So that's very easy. Just we have to push it and just give it a shoulder like a You can see the affordance of rotating saw on the lathe. We have a convex lathe. So it took us about 2 months to develop this. And then we needed 256 of these pieces. Right? We did quite a lot of testing and prototyping, and then it actually took us 6 minutes to make a component. Okay. And we got down to the tolerance of less than a millimeter, which is completely unnecessary with green timber, but anyway, it's really good to have. And then what we did is we made a hole in the wall. We put a slide in, and then every 6 minutes one of these components comes out to the door. So this shows you really the complexity of the geometry, how diverse it is. If you compare this to dimensional timber, right? And this is the workflow, this is the scripting, right? So the thing is, when you can draw a circle, you have a center point, you connect all the center points, and then you have the central line of this component, which is the name of the game really in this exercise. And then for every piece, this tenon geometry, which is the tool part for the robot, just need to be moved onto that central line, right? So that just takes seconds once you've done the scripting. So we are not really nostalgic. We like embracing technology, but we're also very critical about it. We don't believe in this blanket approach that everything is done digitally in the software, in the modeling software, and then you go build that model. That's really painful. Everything is wrong, you know. If you do it the other way around, you just make a sketch and you let the material inform. Because all these projects, I would say, the material is leading. This is very easy from a designer, right? The material does all the hard work. We're just playing with it, right? We learn through making. We build generations. So you see the top, maybe? First generation. I gave this, so when we were building this lovely roof structure, I gave the students 2 hours to make the first model of the tetrahedral, which is kind of the base model of this, mathematically. 2 hours, there's a bit of duct tape, hot glue gun and some sticks, go make it. Right, it was very wobbly, but you have a physical reality that pushes back, and that's really important. And then, you know, like 6, 7 generation, we have the final building. So we incrementally resolve the problems. We don't resolve them all in the digital realm, and then find out, oh, that's not really working, you know. So we learn it incrementally. We resolve problems incrementally. And then this is us assembling it, and then there's no mechanical fixings in this structure. So it's like flat packable, if that's a verb. Yeah, everything is interchangeable. The only problem, it weighs about 4,000 kilos, so you need a bit of a crane to kind of put this thing together. All the projects I'm going to show you, they all need planning permission, they need to meet building regulations. So in order to do that, we work with Arab, who are a world-leading engineering company. The interesting thing is we don't pay them. We have a lovely relationship in kind. So they sign off all our buildings, help us with the structural resolution, and then they can come and play in the forest twice a year. And we build stuff, right? But they helped us with this, and then they give us this lovely Newton value for every threaded rod. So we have to tension this by hand. It's really important for us that the building has a memory of the forest. So this is the thickest of the forest. This is like you're looking through the branches, right? So then we spend these 2 glorious weeks on site, assembling it. And this is what the structure looks like now. Okay, so that's an example of working with natural geometry. So I want to show another example where we work with dimensional timber, where we look at practices of glulam and CLT. so let's unpack that project a little bit. The way we start is when we write a brief, we can't go, hey guys, there's a forest, could you make us a building? That's not enough constraints to work within. So generally what we do is we give them a sketch and we define the workflow that they have to use. So we don't tell them if this is a section or an elevation or a plan, for them to work out. And then the workflow is they had to work with CLT or glue lamp practices, and they have to use Latoya with a bandsaw attached to it, and then off you go. Okay. Now, this workflow is not an accident. It's really thought through because this workflow is perfectly scalable. So the students would make these models on the CNC machine to come as close as possible to the eventual workflow. So I showed you with the field station, we work with generations. The field station, 7 generations to build. I don't know what generation this is, but they build the models, and then we analyze them, we unpack them, and we annotate them physically, and that's the information for the next generation. Now, I am definitely sure that the students have not forgiven me, because this building holds the record for 35 generations of redesign, and this is the final model, right? We had to go through all these iterations basically because the investment in material and time to make these components is so great that we have to make sure we had them absolutely right. So we worked through complete detail. As an architect, you will develop, you will produce data and pass that on to the contractor to fabricate the building. At Hooke Park, and I'm sure it's the same here, it's a really rich culture to be the fabricator yourself, to make things yourself. So we produce the information for construction, and because everything is internal, this is not only informed by engineering information and production information, this is informed, if you could just make out the little red kind of drawing in there, that's the bandsaw. So this is fully informed by the tool that we will use to produce it, and that closed loop is really important. Latoya is great. KRC2 150 for your robotic nerds. That means you can have a payload of 150 kilos and move at 2 meters per second without losing any positional accuracy, which is wonderful, but he only has a reach of 2.5 meters. These pieces are in excess of 5 meters. So a lot of the research is about positional accuracy, right? So we could do a cut of 2.5 meters, and then we have to move the material around to continue the cut. So then we have to produce these kind of drawings, which are highly, this is choreographed information. This is a dance between robot and timber. So we have to move these pieces and relocate it to understand that we can do these cuts. And you can get into these really quite complicated geometries where your robot is called singularities, and your robot is fully folded up and is really mathematically difficult to work out. A lot of the things that we do, there's very little precedence. So we do a lot of break testing to destruction, some of our favorite subjects. We enjoy failure, because then that's where we learn most. We think we live in a risk-averse society, so we like to take a counter position and encourage people to take risk. When something goes wrong, that's when you learn the most. So we encourage our students to fail, but they just have to fail fast, so we can learn a lot. So this is us testing this closed cell geometry, right? We call these near net geometries. So when we glue up this cell, we try and get as close as possible to the final geometry that we want. And then Latoya, as you saw in the video, just cuts away a little bit less than an inch. So you have very little waste material. Anyway, when we're trying to break this thing, Arab will give us a loading value that we need to reach. So in the corner, you could just make out our telehandler. This is the biggest tool that we have on site, 8,000 kilo vehicle, which tries to break this thing. So we introduce a load cell and then we pull it, and we will introduce targets. So when we're scanning this stuff, we have a data value of the forces that's pulling on it and the deflection on the load, okay? We didn't manage to break this one, which is fine, as long as it passes the values that Arab prescribed, we're in safe territory. So this is the primary skeleton for our Wakeford Hall structure. This is the work, kind of 12 months with 7 students. pretty intense. It's really complicated geometry, right? And our program runs for 16 months. So people live with us in the forest for 16 months. We work with them 5 days a week, 8 hours a day, 14 hours a day, depending where we are on the schedule. So what's interesting about a 16-month program is there's 4 months of overlap. So the senior cohort is graduating and there's a new cohort coming in, right? So the senior cohort built this primary structure, and we asked this next cohort to develop the facade system for this. You go, where do you start? Okay, where do you go with this? This is like, look at those nodes and those connections. The geometry is really quite something, right? So this is where our scanning technology comes back in, right? So this is scan data, right? We are not really that interested in design data. We are interested in information as built, okay? We are interested in the digital model for this image. This is really interesting. This is where we overlap the design model with the scan data of the actual built reality. So we understand where there is slippage. We all make mistakes. The material behaves, expands, contracts. So we have to understand that variation. And with that information, the students built the skin, okay? So that was phase 1, phase 2. I'm going to skip phase 2. I'm going to show you phase 3, which is called the tree in the truss. So this is, inside here is that timber skeleton. We like expressing the structural system. And then the students just built this project called the tree in the truss. And we are hopefully just after Christmas installing the roof for this structure. This is a hybrid structure. So it combines natural geometries with engineered timber, okay? I like showing the brief. So we give them a little sketch to kind of say, okay, this is what you need to build, work out the workflows, those are the, and then, you know, it's really important because time is such a precious commodity, right? We need to build this thing. We need to be able to move as fast as possible. So that's why we prescribe quite a lot. But just to kind of set the constraints so people could be creative within that, right? So these are the kind of first gestures that they do from that drawing, and as usual, I will show you a movie of what happened next. Doesn't like my videos, I think. Never mind. So this. Let's try this old trick again. Thinking about it. Hey. Okay, so I shortcut the video. That's fine. Okay, so this is the structural logic. So the component that you just saw, this is the foundation. This is done with a big industrial chainsaw on the robot. This material is cedar. It's really resistant to moisture. And we have to introduce this material because the beech trees are very susceptible to moisture, right? So we have to isolate them from the moisture. So in the total structure, we use 10 of these trees. there's these forking beech trees. Now, each of them is unique, right? They all fork differently, which means we have to make a bespoke glue lamp component for every one of these forks to structurally reinforce it. And then we make quite a conventional truss from that. Okay. The leading principles when we design is assembly and disassembly logic. We don't believe that the wrecking ball is the answer to take our buildings down, right? So if we have failure in a component, we want to be able to replace that. There is no steel in the structure whatsoever, which is quite crazy for something of this size. And the only thing you need to take this building apart, every component, is a mallet, is a hammer. So everything is tensioned together with wedges. Right, so you tension it, it pulls it together. If you want to release it, you just pull them out and this thing comes out. It's very important. Right. So these are the forking trees. They're also cut on the robot. And as I mentioned, we work with Arab, right? We work with Arab. It's really amazing to have conversations with engineers. Because every time, when we start the project and we explain them what we want to do, every time they say, that's not possible. We can't do that. And then we know we're on the right track, right? We're doing something which is challenging. Most of the time we win the conversation. In this case, this is a prototype. We took this to the Royal Academy to demonstrate. You say, oh, you said there's no metal and I can see the bolts there, right? This is because we have to take it to central London. We had to put it in the back of the van and then it had to fit into an elevator, so we had to chop it up and put it back together. Anyway, I want to talk about the anecdote with Arab because I think we're poets or artists. We really like this idea. Look at this branch going out of plane and coming back in. Right? We really want to keep down output. No way, you cannot do that because now all of a sudden you are not talking about compression, you are talking about rotation, which is incredibly difficult to calculate. More so because this timber is green. So it means this has a moisture content of say like 60%. This stuff, when you look at glue lamination, when you want to glue the stuff together, you need to control the moisture content. It has to be below 16%. Right. So these things are exchanging fluids and are in a complex conversation. So we didn't win this one. Everything can be plain. And then if you understand the truss logic, it's really quite straightforward, right? Your first piece is in compression, and then the second piece needs to be in tension, right? That's the way it works. It just iterates. Compression is very, very straightforward. You just need a shoulder so you can push on something, right? Tension is very difficult because timber in tension is very strong. The problem that you have is that as soon as you remove material or you drill into it, you make it weaker. Okay? So the video shows it very well, though you have to believe me now. So what we did is we steam bent it and we just splayed the fibers. So we just curve cut it, steam bent it, and then splayed the fibers, and then we introduced these wedges. So we changed the geometry of the timber, right from this to this. And now we can just pull on it through its geometry. Okay? And this was really where all the research is, because these are small bits of timber. And then Arab goes, yeah, okay, the maximum tensile force that this piece needs to take is 4,000 kilos. I thought, wow, this is just a little branch. So again, there's no precedence. We have to build a testing rig ourselves. You can see the lovely load cell at about 2.5, 3 ton. We have an issue. So this is beech, which is a hardwood as I described. Our dimensional timber is spruce, which is really lightweight, very strong, efficient material, but it's a softwood. So what is happening is like we are pulling and the grain of the softwood is collapsing and we pull the structure through it. So we're going, okay, we got a problem. Houston, we got a problem. Obviously from a weight ratio, we could not replace it for a hardwood. So what we did is we put this prosthetic bit of hardwood in just locally So we are locally reinforcing the timber to be able to deal with that force, right? And that's where it becomes really interesting. So this is this laboratory setting where you keep experimenting and testing. And these are the gangsters that we built this with. Absolute joy to work. These people come from all over the world, right? And as I said, they live with us in the forest for 16 months. Okay. I want to show you one more project if you have a bit more patience. I really hope the video works on this one. This project is called the datum. This is not a render. This is a built structure. So we built this jetty into the forest. And again, we just give the students a sketch because there's not enough time to go wandering off for 3 months for all these different design iterations. It's not particularly beautiful, but it tries to set out the parameters that we need to work with. This project is really important because we are really for this project, we don't have to cut down a tree, right? We go and do this practice of high pruning. So we cut the lower hanging branches from the tree, and that gives us our source material. We're really interested in indigenous practices. We don't believe that in this day and age anyone should cut down a tree, to be honest, if you can help it. Okay, so let's have a look at what this looks like. Come on. So we're interested in working with crown timber, right? So we're moving up with the tree. So if you look at the standing tree, again, 50% mixed as a component, that's seen as highly efficient. So we're trying to work with the missing 50%. So the previous project was looking at these secondary branches. We're now looking at stuff which is 20 millimeters, like 1/8 thick. No one looks at that and say we could build with that material. this is the material that we're working with. So remember, we don't cut down the tree. What's really interesting, well, I like this term, in forestry, this timber is called juvenile timber, right? So it's wild, untamed. It's the teenagers, really, of timber. So we are really excited about the potential of this project because now we don't, I plead guilty for this fetish of working with a robot, right? In this case, all the intelligence sits within the little jig that we make. So we're really interested in practice of community, working with communities. The only thing you need to build this project is the jig and a bouncer, right? Which is quite a different connotation than saying you need a whole robotic thing. Anyway, I like the approach of this one because we are working with a very basic cell. Okay, this is the symbol cell. Working with complex systems is really difficult to understand simplicity. Right? If you can work with a simple cell, it's really difficult to introduce complexity. You just multiply it, but you understand the basics. And this is the basic cell that we work with. And we, as I said, this is the jig that we've developed to cut this. So this is the logic. We just keep stacking them. This stuff is so small that you cannot cut a timber joint into it. You only have an inch of material. You can't remove anything. So they all have to be held in place just through its geometry. So this whole system works in compression. Okay. And again, it's the same principles again and again. This is the very first jig that we make to cut these geometries. It takes about 2 hours to make something like that, maybe, right? And then we introduce more intelligence into this jig, right? So you can see a bit 3D printed components. We kind of understand its function better. So we need a little sledge so it runs on a track so we can repeat it. So we make 3 of these. Most time is taken by loading up the subject into the carriage, right? But if you have 3 of them, you can prepare them, and it just takes less than a minute to cut this. Again, I spoke about stepping back as a designer, right? We do not determine the X, Y, Z of this jig. So what we did is we took a scan of the trees, and we did an analysis on tree morphology. So how do these branches, what are the angles, what are the dimensions? And then we looked at the most frequent occurring geometry, and we accepted that as the basic cell to work with, okay? So this is what this study does. And then here they are. They're all locked, they're all leaning against each other. And this is a jetty, like a boardwalk, right? So all these pieces are going to be in compression. And this is the magic bit of Dyneema. Dyneema is an interesting engineered material. It's about 10 times stronger. So it's basically a cable. So with a turnbuckle, we can put this whole thing under tension. And it's pretty much like you have pre-tensioned concrete. If we want, we could turn this thing into a banana, so you can anticipate a load scenario, okay? And this is us installing it on site. Okay, and maybe, so as I mentioned, we're really interested in this as a floor system or a roof system. We're really interested in working with communities. We'd love to go to Kenya or anywhere where there's lots of trees and lots of communities. We can develop this. The stupidest thing you could do with this is put it outside in Dorset because it rains 270 days. And this is beach susceptible, but we're a laboratory, right? We don't say, hey, this is going to fail, so we're not going to do it. We're intrigued by how it's going to fail. We want to learn from this as a system, right? Because this project contains ideas of pedagogic models, but also ideas of full circularity. We believe these branches takes about 3 to 4 years to grow. If our structure can have a lifespan of 3 to 4 years, this thing is built to assemble and disassemble. So we just released the tensions, and we could take this soft tissue out and replace it. So I'm sure you're all aware of these beautiful models in Japan where they build the ISA temple, they rebuild them every 40 years to teach the craftsmen, the next generation, the practices, so all these, the knowledge is integrated. I'm very happy to teach the next cohort in 3 or 4 years to work with this again, right? So there's pedagogical models, there's ideas of material efficiency, and this is the other thing that I want to say about this project. This is not about material efficiency. This is not about minimum amount of material for a maximum span. This turns this whole equation upside down. This material is in abundance, right? It's absolutely everywhere. So we are looking at models of density, right? We're looking at models of redundancy, right? Because we could pack this as dense as we want to. There is no shortage of the material. No one works with this. We can have tons and tons of it, right? You have a different kind of problem when you say, oh, we have all these beautiful oak prime beams, right? Everyone wants those, right? That's expensive. This stuff is for free. Okay, so it's really important to look at these things. And I just want to show a couple of models, because there's an inherent beauty of these natural geometries, right? And I like this image because it's a beautiful summary really of this project. So we look at the crown timber, and we can kind of identify the branches that we want to cut out, and those are all the suspects kind of laid out, and then we will assemble them, right? And you might have seen throughout the presentation there's this idea of a continuous and accumulative research. We're trying to kind of keep developing the work and kind of pushing it to the next level and adding complexity. So this is a horizontal structure. So we now asked our students, say, hey, well, how about if we turn this vertical? What happens? Can we use this as a facade system, you know, as a curtain wall? So this is very fresh. These students just finished a couple of weeks ago. So this is an example of a large glaze kind of, this is a prototype for a door, but it investigates the potential as a hanging facade structure. Okay, so there's a little bit of metal, but it uses exactly the same jig as in the previous. Right? So we're trying to accumulate the research and kind of keep developing it. Right. You might see what is this structure doing? Right. So we have this jetty that goes into the forest. It sets out this beautiful horizontal plane. And we're very privileged in Hooke Park. Lots of people want to come and stay with us. So we're developing camping facilities because we can only have 40 guests staying with us. But in the summer, we can kind of double our inhabitation. So the jetty is a walkway that helps with our camping facilities, and they will give us access to the showers. We call the showers the wild thing, and this is where we kind of are at the moment. So it uses similar kind of principles of making fabrication. This is us installing it. What I like about the wild thing is we go onto the jetty, there's 2 drawbridges for you to get into the shower. When you cross the drawbridge, you turn around and you pull up the drawbridge that becomes a door that provides the privacy for the shower, and no one can kind of get access to it. So there's these beautiful kind of poetic notions. So we love working with timber. It's a really amazing material. Everyone goes, timber's going to save our built environment. It's a bit sad news, there's not enough timber to go around. So this is why we do these exercises. We need to look at material efficiency. How can we think differently with the material that we have, okay? Timber is good at lots of things. It's really bad at a couple, right? So it can't deal with relationship to the ground mostly, or wet conditions. So we are looking for good bed partners. So we found amazing wild clay locally in the forest. So we're developing these clay practices. So we just worked with Molly, who's our ceramicist, on developing this slip cast tile. We just made 100 of them. And these are for our, it's quite a funny story. This is for our outdoor toilets. Kate, she's the head of Hooke Parks, and said, outdoor toilets have such a bad reputation, right? So what I want to do is we need to make the best, most amazing outdoor toilets. So people, when they come to Hooke Park, they say, you've got to go to the toilet. It's amazing, right? So we decided to make these really beautiful tiles, and we're going to go all in, you know. We're going to make these tiles, they're going to be amazing. They're like a brick, double-sided, really beautiful slip cast. And then we're going to give them, it's going to be like full Russian oligarch style kind of luxury toilet. So we're going to give them this high black vinyl. These are the very early prototypes that we just did. And we do some blood splatter gold luster in it. So the light's going to shine and it's going to be the most amazing toilet. Anyway. I really believe in this. You know, I really believe that the future belongs to the few of us that are willing to get our hands dirty and go playing. So, architecture is a broad church. There's lots of subjects, lots of ways, lots of different practices. If you're interested in videos or games or animate, there's lots of different ways you could work with architecture or within architecture. We are really interested in working with the material because we're just playing. You know, I hope if there's anything that you take away from this lecture is that we are playing with the material and there's lots of fun, right? When you understand the behavior of the material, you can actually really work with it rather than against it, right? And I'm going to be unashamed about advertising my little summer school. If you want to come and play with us, we run these little visiting programs that you can come and play with us for 2 weeks in the forest. We just drop you into our workflow. We have great parties, we have great food, and you can kind of experience our practice. Thank you very much.
I think we have some time for some questions, if anyone has any questions. Can you project or do you?
Hi, my name is Wang, and I want to ask about the datum project. So when you harvesting like a bunch of branches like that, right? Some of them are like chunkier, some of them are like very dainty. Like, do you decide like which one go where? Like, how does that work?
Oh, interesting. No, because when we use the jig, we return them to fixed geometry, right? But it's an interesting question because I guess you could, if you understand the complex loading system, you could put the chunkiers where there's more loading and the smaller ones inside. But this is a model of redundancy. So there's lots of little ones working together, right? And it's really nice because this stuff is freshly harvested. So this is green timber, juvenile green timber, right? So it hardly has any hardwood in it. It means it will shrink and move and adjust, right? But this is the beauty of the tensile system. So we could just go rattle it if it's loose, we tension it a bit more. You know, if we hear things crack, we release the tension a little bit. So it's really fine tuning as you go along.
Thank you.
So on the bridge, I had two questions, sorry. On the bridge, you said that the like abstract branches in the middle, you can like switch out every 3 to 4 years, right? So when you switch it out and like you take out the old ones, bring in the new ones, can you use the old ones for anything else? Like not necessarily like a building, but like do you like recycle those or like can you use like you like extract the water from them or?
Well, really what we do is they are unaltered, they are untamed, so they are not contaminated. So they just go back to nature. They become, there's an ecological value to return the material. The reason why it breaks is probably because there's moisture or insects have eaten them or it's starting to rot. So the structural integrity has disappeared. So we wouldn't necessarily look at reusing them because they are, first of all, they are zero value, as in they are a waste product, right? So we've already used them, and because its structural integrity is gone, and because it's so ubiquitous, it's everywhere. right? So we could just as well make new ones.
I'm so you talked with like each project about how you like started with a sketch and like it was kind of like an arbitrary sketch. Can you like talk a little bit more about either the sketches or how you went, like the students went just from a sketch to kind of a concept?
So the sketch is there to help set up design constraints, because there's a lot of figuring and finding out to do, right? So we're trying to set up just the right amount of constraints to allow a maximum of creativity. I think it's a fallacy to believe that all the reward sits within the design phase, right? So pretty much all the sketches are done by myself and the team. So we set out the research. The great advantage of that is we can start just like that, right? We give them a sketch, we give the brief. Half an hour later, we're in the workshop making the stuff, right? And this is probably where there's a massive variation between practice and education, right? Within a design studio, you will spend 3 months or like designing stuff and going back over it, right? We need to compress that time because we need to do the physical building, right? So we really want to move away from this idea of the star architect, right? The AA is really amazing. They produce people like Zaha Hadid and Norman Foster and Rem Koolhaas and all these star architects of last century, which is a really dangerous model. We believe the biggest thing that people learn when they come to the course is how to work together. And this is very difficult, right? People come from all over the world, but it's incredibly rewarding, right? All the things that we did, you cannot do that as a sole practitioner. You need to work together with a team, right? And that's why the whole context leans itself towards it, because you know, we don't see our students for 1 hour a week, right? We see them every day, all day, right? And we sit with the team and we work like a practice. Some call us a tribe or a commune, you know, whatever. But it's a really different way of working. And this collaborative nature is so important. And I think it's maybe it's a model for the world that we have to learn how to work together, you know. So it's really important. It's the single most important thing that the students do. Sorry, I'm not.
Do a lot of those students come from various backgrounds, so structures or furniture making and collaborative, and then are you starting to see impact on practice? And I mean, you showed an example, but talk more about that.
No, people come from all over the world. We have 2 programs. The master MR is 16 months that they live with us. That one is really tightly regulated. People have to finish their 5 years of architectural education. That's the model in Europe. Maybe it's 4 years here, and then they can come and join the course. The MSc is a Master in Science, which is a bit looser from Access, so we have a lot more kind of engineers or artistic kind of backgrounds, and they are with us for 12 months. But they are pretty much all working together on the same project. And this is where it's really interesting. You know, it's one of the perks of my job is to do the admissions, right? And people go, oh, you must be looking for all these, you know, macho workshop types. So the first person I'm looking for is someone with project management experience, you know. If we have anyone in there, well, you're in, buddy, you know, you come and join the team. So we really want, you know, I want 1 or 2 digital wizards. I want some with real design, eye, and integrity. So I'm putting a team together. It's pretty much like a football team, right? I'm sorry, my analogy might not work here with American football, but I can't do anything with 11 goalkeepers, right, in soccer. They have to have different skills. And it's pretty much like putting a practice together. So yeah, the different backgrounds are very important. and we have a very long kind of like winded process of admissions. You know, we try and get them all to the site. We need to meet these people because we need to live with them for 16 months. We need to get along, right? And it's really important. So we do lots of interviews and conversations, and we meet each other and all that kind of stuff. So yeah, it's really important. That's a good question.
Hi. What are you doing with the twigs and the sawdust? The tiny pieces? What are you doing with the tiny pieces?
Well, at this moment, we're leaving them in the forest because of the ecological value for the insect and the soil health. That's important as well. And then the sawdust, we've been compressing it into bricks, but we have a zero waste policy. So we have a wood chip burner. So if we make mistakes, we chip it up and it goes into our heating. So we have exactly the same like your central heating, but it's the scale of a campus. And it heats up this big barrel, and we have this underground vein network of pipes that go to all our buildings, so they're all underfloor heating. So our workshops are nice and warm all year round. And this is the other thing, our facilities are open 24/7, and we treat our students as adults. So we kind of, they can use a workshop. Okay, but we switch off 3-phase at 5 o'clock. No one needs to be playing at 3 o'clock in the morning, right? So there's a little bit of regulation there, but we try really to treat everyone as an adult and be a really respectful environment. So I think that those things are really important.
Here, guys, I'll just take it off. For the project that went 35 iterations,
Yes.
kind of stuff, right? So our students get bound by a timeline and a deadline that they're trying to work toward.
Yeah.
And you have the luxury of the laboratory that you can continue to revise. Andrew, what is or what was the creative insecurity within that project that said, no, let's do it again? Was it a metric of like, let's test this till we fail it? Or was there something not quite right that you kept digging deeper to find? But what made 35 good and not 34? Why not 36?
Well, that's a great question. I have to go back because this project was 2016, so it's a while ago. But it needs to meet lots of different criteria, right? So things happen concurrently. So we're developing the design, we're reworking the small stuff. At the same time, we are building one-to-one prototypes, and they inform each other, right? And then we do break tests. We have the engineers coming in. So all this information needs to be massaged into these components. But as I mentioned, the most important thing was the material investment and the time to make one of those stock materials was really expensive and extensive. So we could not afford it to go wrong. So we needed to debug all possible issues. So it was lots of stuff of like, oh, everyone agreed this geometry is wonderful, but we can't cut it with a robot. And so you have to go back and adjust it. So it's all this continues back and forward. And there were so many layers to this project. Well, one of the key constraints was working with glue lamp. If your glue sets within 30 minutes, right? If you cannot clamp it up within 30 minutes, we lose structural adhesive, So all these things are like, that's such an abstraction when you're in your design studio and you're drawing your geometry, right? But I have lots of little movies where I'm standing there with the stopwatch and we do what we call dress rehearsals. And all the boards are cut and we're ready to glue up, but we do a dry run. So if the students can clamp it up without the glue, under 25 minutes, that's it, we're ready to go. If you can't do it under 25 minutes, you need more practice, we do it again. So there's a lot of these kind of abstractions which are not really part of a conversation when you're in the design studio, just certain practicalities, right? Everyone might have agreed, engineers, the aesthetics, everything looks great, but we can't get it glued up under 30 minutes. It's like, well, okay. So yeah, it's quite interesting. Keeps us on our tiptoes.
Other there any other sister organizations like yours? Anybody else do anything like
Well,
this?
you guys, there's Yale, there's a lot of them in the States, obviously in Alabama, Real Studio kind of come close. But I guess we're quite specific because we inhabit the forest. It's so focused on the material. And I think some people see that as a constraint, but there's a real richness to, because we're exposed to this timber production and we understand it inside out, right? It's important to say that we don't make any requests on the forest. So we have two foresters that manage the forest. We don't say, hey guys, we need 200 running meters of oak. That's not how it works. They have harvesting schedules and we work with the material that comes from that. That's why we're always really excited when there's a storm, because then there's storm damage and we have species that we could work with that we didn't expect to. Right? So there's this kind of continuous strangeness of having that ecosystem that is full of surprises and is quite rewarding.
Question, how does your institute work with making, or does it try to make things like commercially viable and connect with industry? Because this is, very beautiful designs, but can it be built in a cost-effective way where it can actually be purchased in other than very specialized situations?
Yeah, that's a great question. Thank you. Okay, there's a couple of things. First of all, we work with zero value materials. So industry go, okay, where's the profit margin? Okay, so that's a difficult conversation. And then this is something that we're working on. We have lots of practices come to us and say, oh yeah, you guys, that's amazing, right? But we cannot buy a whole tree anywhere. Where can we go to buy this, right? So that's something that we try to address. So we are developing our timber production to be able to sell these unique components to other people. And then the third thing, which we're working on really hard, is we're setting up a research practice. Because all these systems are ready to be deployed off-site, right? So we have 5 or 6 commissions that we are ready to, but at the moment, as I'm sure Shat will put, like the paperwork about insurance and all those kind of things as well is slowing us down at the moment. But we are working on off-site projects, which is really exciting. The closest that we are getting is we are prototyping. So we're making large components for architectural practices. And say, can we test this? Can you make this for us that we can actually do some proper bending tests on it and take it off-site? So that's the closest that we are now, but it's very exciting to be able to go off-site.
I think we have time for one more question.
Oh my God, it's a Jedi.
So, can you hear me? What was your most valuable mistake or failure? Sorry.
Wow.
Something that you learned and then you use every day.
I'll talk about the exercise. We did the first exercise with our students for them to make sawhorses. Do you guys know what a sawhorse is? Okay. So we just gave them a round log and say, here you go, make a sawhorse. Just to expose them to the embodied energy that's required to get two-dimensional timber and all this kind of stuff. So they spend 2 months, 6 weeks making this sawhorse. And then now we're going to break it. So they're all really precious because they just spent 6 weeks making these really beautiful things, right? And then, well, we said it has to, I can't remember now, it has to withstand 1.5 ton of load, right? If it can withstand that load, we could use them in the shop. If not, it's going to break, right? So everyone was really, really scared that their structure was going to break. So the first 2 or 3 survived fine. And then the first one broke. The first was a little bit sad, but then we did a forensic analysis. So we go and look why did it fail? And it was not because of how it was made, it was because of the structure of the timber. So where the nuts were, where the grain runoff was. Right? And after that first one failed, everyone wanted theirs to fail. They didn't want it to kind of survive the structural loading. They all wanted to fail because you learn so much more when things go wrong. And this is really important, you know. So I'm not sure if it perfectly answers your question, but it's something which was really instrumental, kind of demonstration why failure is important.
All right, well, thank you so much.
You guys did pizza. Looks nice.
Amazing work.
Oh, thanks, I hope you enjoyed that.
Inspires me to think about how I did some of the stereotomy. I love
Not ever. Yeah, yeah, kind of a mixture of stereotomy things and make the stuff